Welcome everyone for another video lecture on convolution codes. In the earlier video, you were introduced with the basic structure and functionality of convolution codes. This video describes various methods to represent convolution codes. This is just a compilation of various methods to represent convolution codes and find the output from the encoder. An encoder output for a given structure of convolution code for any input given sequence can be found out by either state diagram, tree diagram, or trellis diagram, or it could be with polynomial representation. With polynomial representation, it is a representation of convolution in time, which is extensively used in machine algorithms. For any computer tool using machine uh, 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 for any machine using computational algorithms, convolution in time or polynomial representation can be utilized. So without much ado, we'll begin with representing encoder output with state diagram. This is one of the simplest methods and known method to represent the encoder output. This is also called as impulse response or instantaneous response for the incoming bit. This is an example that we have taken to understand and try to represent in a various types. Say this is 1/2 encoder where for each incoming bit you will have two output bits, and this has got a constraint length of 3, and the output will have two modulo adders, and hence we can say this as rate half and with a constraint length of L is equal to 3. K is equal to 1 here as we process each bit one by one to produce two number of output bits. As you know, generator polynomials are described whether the output is connected to the input memory register. For the output first bit, the middle memory element doesn't have any connection, and hence the generator polynomial for the output bit is 101. And for the second modulo 2 adder output, it is generated with the inputs from the three memory elements. A number of states is calculated or described as 2 power k times L minus 1, where the first bit here or the first memory element is not counted to find out the number of states, where it is reserved for the incoming bit, where the incoming bit is pushed through this memory element, and hence with two memory elements we will have four number of states. Let's try to represent in a state diagram. Before that, we should tabulate for various combination of input bits and status of memory. We should find out the various combinations for the output bits. That can be easily done by using state transition table that you might have done in your basic digital design courses. We'll redo the same because it is one of the simplest possible way of understanding or finding out the encoder output. The state transition table can be tabulated with input bit, the current state of the memory register and register content, and the output bits. And also it has got next state as well, where what happens with the content of the memory or the status of the memory register for the next timestamp. If you take an example with the initial 00 being the content of the memory or the state of the encoder, if the incoming bit is 0, so all the first row will be 00 because nothing will change until and unless you flip the bit to 1. The incoming bit is 1. If the current state is 00, the memory register content would be 100, and the output is found out by using the output of these modulo 2 additions. As you know, if this is 1 and if this is 0, the addition of that will give you 1. If this is 1, 0 and 0, the modulo 2 addition of all the three contents of the memory register will give you another 1, and hence the output of generators would be 1 and 1 each. And for the next timestamp, since it's a shift register, you are going to right shift the current state with the incoming bit. If it is right shifted, it will be a 0 on the rightmost bit will be flushed out, and hence you'll have next state to be 10. And accordingly, the process continues. I'm not going to describe every row of the transition table here. It could be very trivial. We can continue doing the same for any other combination. which is very evident from the encoder diagram, encoder structure, and with a different combination of input bit and current state. With the help of state transition table, we can easily draw the state diagram where it kind of a summary of, or in a compact form we can represent the state transition table. As you know, a state transition diagram will have four different states of the memory register: 0 0 0 1 1 0 and 1 1 being the four states which are represented as a four blocks here. And with the input bit varying, say if you are current in 0 0, if the incoming bit is 0, the output would be 0 0. So 0 slash 0 0 represents input slash output, and the arrow indicates the transition from one state to another. So in this case, since as long as the input bit is 0 and the current state is 0 0, it's going to in the self loop itself. So with that understanding, we can find out the different paths here. From 0 0, the state will change if the incoming bit is 1. So input bit is 1 here. The output would be 1 and 1. So slash 1 1 represents the output bit combination. But with that input bit being 1, the next state would be 1 0. And hence it has the transition from 0 0 state to 1 0 state has happened. So you can continue doing the same like for other combination in the state transition table. We can take, as a last row as an example to have completion of discussion on a state diagram. So let us say that we are in the state 1 1, and if the incoming bit is 0, so if the incoming bit is 0, the output in the state transition table is mentioned as 1 0. So for 0 0, the output is 1 0, and the next state is 0 1. So the transition from 1 1 to 0 1 is shown with an arrow. If incoming bit is 1, if the current state is 1 1, the next state will also be 1 1 as indicated by the self loop. However, the output will be 0 1. So output is represented as 0 1 here. So rate half indicates incoming by out number of output bits. So it's 1 by 2. Okay, so this is one of the basic methods of representing encoder output. So with the help this gives all the combination in the transition table for a set of given input bit stream, you can find out what would be the output. Say if the incoming bit is 0 1 0, so first it starts with 0, which output is 0 0. If it is 1, it would be 1 1. Say if the next bit is 0, the output would be 0 1, like that. So output of encoder would be 0 0 1 1 and 0 1. Likewise, you can make use of state transition diagram to find out the output of the convolution encoder. There are other methods as I had listed earlier. So let's pick up the next one, which is in the form of tree, and hence it is called as a tree diagram. This is basically an unbounded evolution of states in time. So it goes on growing. The tree grows on goes on growing for infinite amount of duration in time scale. It's just it's an alternate representation of the state diagram itself, wherein you begin with the current state as 0 0, and it branches into two ways, with 0 representing one of the input bit and 1 representing another variant of input bit. So for the current state, if 0 0 is the input, it will be output will be 0 0, and so on for forever. But if the input bit is 1, the output is 1 1, but the state is represented as C. Here the state is not mentioned exclusively, but it is encoded as A, B, C, D accordingly for 0 0, 1 0, 1 1 and 0 1. So this is with the grayscale coding. We have represented the various states of the memory as A, B, C, D. So this will be utilized again in forthcoming videos, where A, B, C, D would be easy to understand the nature of the state instead of representing in a binary fashion. And as you know, from 1 1, again if the incoming bit is 0 and the output would be 1 0, like here. If the incoming bit is 1, the output would be 0 1. So state represents B and D here. So this is a self loop which is represented as state D. So this tree keeps on growing forever as long as you try to stop it. Unlike a state diagram where it looks like it is in a loop, but for a tree diagram, it goes keeps on growing until unless you stop with the number of input bits incoming to the convolution encoder. But remember that the upper branch represents incoming bit 0. The lower branch represents incoming bit 1 at any node in the tree. Okay, that's how you try to represent in a tree diagram, which is an extension of a state diagram. Alternatively, you can also represent one of the famous types known as trellis diagram. So this actually depicts evolution of states in time. So this will have a certain, we can say that is a bound, but it's a kind of an unbounded evolution itself, very similar to the tree diagram. Uh, you can either make use of state diagram or tree diagram to obtain trellis diagram. Trellis diagram is very similar to the tree, but it represents the timestamps in the on the x-axis. Here, status are represented in y-axis. So 0, 0, 0, 1, 1, 0, and 1, 1 being the states, different states of the memory, the 4 states of the memory register, which are coded using your gray coding technique. Say for the first state, if incoming bit is 0, the output will be 0, 0. And again, if the incoming is 0, it will be 0, 0. And it keeps on following the straight line for forever for incoming bit as 0. So the darker line indicates the incoming bit as 0. Here, unlike the state diagram, we don't represent uh, incoming bit here. So we represent by separating the arrow with the dark one and dotted ones. The dotted ones are the represent dotted ones are the representing if the incoming bit is 1. Say at 0, 0 state, if the incoming bit is 1, the output is 1, 1. So if, from the state 0, 0, if the incoming bit is 1, the output bit is 1, 1, and the next state would be 1, 0. 1, 0 state is here, and it moves from this state to this state. And from here again there will be 2 more branches for incoming bit to 0 and for incoming bit to 1, and from each of those we'll have another 2 branches, and this trellis keeps on growing uh, as long as if you have no limits on time and if you have infinite number of bits incoming to the encoder. For any particular combination of sequences of incoming bit stream, you can trace in the trellis diagram to find out the output bit stream. All the 3 representing the same encoder or the same convolution encoder structure, but represented in a very different fashion. Trellis diagram is the one which is used extensively, which can be plotted using any computer algorithms or any mathematically computational algorithms. Uh, Before we proceed on to taking any other examples, we'll complete this with another famous representation or which is used in computers extensively, is in form of polynomial representation. This, as I said, this also can be said as it's a representing convolution in time. With a little different example, here I have considered rate 1 by 3 convolution encoder with a constraint length of 3, and the input bit stream is processed bit by bit, and hence k is equal to 1. As we know, there are 3 generators here. We can accordingly we can write 3 generator polynomials. So the 3 generator polynomials can be easily written, and those generator polynomials, when convolved with incoming bit, will generate the output codes. So the code words here, superscript 1, 2, 3 represent the 3 bits of the encoded output, and the encoded output or the code words are generated by convolving the incoming bit stream, which is represented as u, with the generated polynomials. Since each polynomial is represented as g1, g1, g2, and g3, and accordingly you have 3 bits for the code word. And the corresponding code sequence in general can be written as, say for first timestamp, the subscript represents the timestamp or at t1. Superscripts represent different bits in the code word. So at first timestamp, you will have 3 bits represented as C1, C2, and C3. For the timestamp T2, you will have another C1, C2, and C3, and so on. So you can represent code sequence in this manner in a mathematical way, in a vectorial way, in other words. The convolution operation, as we have mentioned here, to generate encoded outputs, it is equivalent to multiplication in the transform domain. If I try to, this is in the time domain, convolution is in the time domain. If I take into transform domain, it could be frequency domain, or it could be Z domain, or it could be D transform. Here it also can be called as Z transform in some of the resources. So you can say it as a D transform, which is represents the delay. So here there is no delay, which is 1. Here it is 1 unit of delay, and it is D. Here it is 2 units of delay, and it is D square. So D power 0, D power 1, and D power 2. If you try to represent the transformation from time convolution to frequency domain, which will be simply multiplication in that transform domain. If you try to represent in a transformed domain, we can write u of d. U of d is incoming bit stream as u suffix I d power I. So if it's a message sequence is say 101, it will be accordingly u1 into d power 0 plus u2 or u0 d power 0 plus u1 d power 1, and so on. So according to the incoming bit stream, whether it is 1 or 0, this will get multiplied or doesn't multiply if it is 0. We'll take certain particular example and try to express in terms of polynomials. Once you have generated this u of d with information of bit sequence incoming to the encoder, we can multiply with the generator functions or the generator polynomials, which will give you impulse responses. So the impulse responses are obtained by multiplying u of d with each g1, g2, g3. Each g1, g2, g3 can also be represented in a d domain or d transformed domain, where g1 of d is simply 1 0 0, since these two are not connected to the first output. So 1 0 0 is represented as 1. G2 of d is obtained, or the second output of the encoder is obtained by adding the first and the last one. Since I have told this is d power 0, d power 1, and d power 2, this will be 1 plus d square. And accordingly, G3 of t by obtained by adding in the d transform domain, this will be d power 0, d power 1, and d power 2, and hence it is 1 plus d square. So these are the polynomials for the generators. And you'll also have the polynomials for the incoming bit stream according to the specific incoming sequences of the bits. And once you obtain u of d and various gi's, you have to multiply these polynomials, and hence it is called as polynomial representation. As I told, all our job is to transform from time domain to D domain. So in D domain, it is just multiplication of U and G. And hence it is called as convolution in time or multiplication in D transform domain. Let's take particular examples and it will be very clear. And finally, the transform of the encoder output. The final encoder output is obtained by picking this individual C1 of D, C2 of D, and C3 of D. Since it's L is equal to 3 is the constraint length of the encoder, all these D's will be replaced by D cubes. And finally, you will get the final output of the encoder. Let's pick one example quickly for the same convolution encoder for the same structure. Let the sequence be 1 0 0 1 1 1. Our first job is to transform this into D domain. U of D, as I told, depends on the incoming bit stream, and since there are 6 bits here, it will start from D power 0, D power 1, D power 2, and up to D power 5. So D power 1 into 1 would be 1 itself. Sorry, D power 0 into 1 would be 1 itself, and D power 1, D power 2 are zeros. D power 3, 4, and 5 will exist when you try to convert into D domain. This is our incoming bit stream polynomial representation. And we know that generator polynomials are 1 1 plus d square and 1 plus d square. When multiplied with u of d, you'll obtain c1, c2 and c3. When you try to multiply with 1, it will be retained as it is. When you multiply with second generator polynomial 1 plus d square, carefully you should observe that when you try to multiply d3 and d square, it is d power 5, and there is another d power 5 that you will be obtaining by multiplying this d power 5 and 1. So d power 5 plus d power 5 will be 0. Only on the factor that these are all modulo 2 additions. So d power 5 represents the same bits. 0 plus 0 or 1 plus 1 would the result would be 0 itself, and hence you don't see any d power 5 terms here. Right? So otherwise, you can see all the other terms when you try to multiply. So 4 plus 2, you will get 8 terms out of this multiplication. When 2 d power 5 gets combined, those will vanish and you'll have only 6 terms. Accordingly, you try to multiply these two polynomials. So whenever you arrive at same powers of d, that term will get vanished. And that's how you obtain C of 1, C of 2 and C of 3 of D's like this. And for our final job is to generate the final output sequence for the encoder. That's what we did for earlier representations as well, whether it was state diagram or tree diagram or trellis diagram. So our job was to find out for any particular message sequence given, we should be able to trace out the output of the encoder using those representations. Accordingly, if this is the output of encoder represented in polynomial, you should be able to generate the output sequence as well. The final output sequence, as we have told, can be written as functions of C1, C2 and C3 of d cubes. So since this is d power 0, d power 1 and d power 2 are LSB, mid bit and MSB. Each C of 1, C of 2 and C of 3 is multiplied by d power 0, d power 1 and d power 2. Since it's a constraint length of 3, these are all functions of d cubes. And finally, you'll obtain the encoded output sequence to be in this fashion. Again, when you try to add two terms of the same exponents of d, those two terms will get vanished with each other. Probably here d power 4 plus d power 4 would have been obtained. If you try to add those two up, that d power 4 doesn't exist at all. That's how you can try to obtain. So just addition of all these would be the output of the encoder. Corresponding to this output, the code sequence can be written as this is d power 0 and hence it is 1. This is d power 1 and it is 1. It's d power 2 and then it's 1. D power 3 and d power 4 doesn't exist and hence 0, 0. This is d power 5 and hence 1. D power 6 doesn't exist and hence it is 0. And 7, 8, 9, 10, 11, 12, 13, 12, 13 are all ones and d power 14 doesn't exist again. So there are 24 bits in the output code sequence. Obviously, there are how many? 6 bits for the incoming bit sequence. Accordingly, you will have for each bit you will have 3 outputs. So you should have so much amount of output in the output sequence, and there should have been 18 bits in the output. This is obtained by flushing more zeros so that you will reset the status of the convolution encoder, and hence you'll have so much amount of length of the bit sequence or the encoded output. So these are all different varieties of obtaining convolution encoded output. Any of the representation is fine to obtain. A few of representation need manual computations of like polynomial representation, for which you need to multiply the different polynomials and obtain the resultant. However, this can also be intellectually used in case of in machine computation in form of algorithms. Before we end up this particular video, which depicts various types of convolution encoded output representation, we'll take one special type of convolution codes, which is known as catastrophic codes. With an example, I'll try to explain what is a catastrophic code. Let's say that this is a 1 by 2 convolution encoder. which is obtained in this fashion, where the first binary 2 addition or modulo 2 addition is from the mid and the last one, and the second one is from the first and second. With this convolution encoded structure, we can obtain the state diagram as we had mentioned. So I'll not explain much about the process of obtaining state diagram. This should be very evident. What we are focusing for this particular example is that if the sequence is all ones, let us consider the input sequence is all ones. It's a very long sequence of all ones. If that is the case, you can see the transition in the state diagram. For if I start with 0 0, if the incoming first bit is 1, it will get transition to 1 0 with the output 1 0. If another bit is 1, since it is all 1, so incoming bit is 1, so it will move to 1 1 state. And again the incoming bit is 1, it will be in the same state. Again the incoming bit is 1 and it will be in the same state. So it will keep on looping in the state 1 1 with output of 0 0. As you can see, the output for the first transition was 1 0, starting from 0 0 state. The output was 1 0. Next the output was 0 1. Next the output was 0 0, and so on. So it will continue with 0 0 as long as the incoming sequence is 1. It will exit this self loop only if the incoming bit is 0. And if you want to reset this convolution, if you want to reset this state of the memory, you can push a few zeros. So 1 and 2 zeros are enough to get back to the original state of the memory, for which you will have the output of 1 0 and 0 1. That's why for the input sequence being all ones, the output would be first output set is 1 0 0 1 and rest all zeros. So 1 0 0 1 and all zeros of long length, and until and unless you try to flush in zeros to make memory getting reset, for which you will get an output of 1 0 and 0 1. So these two for the last 4 bits are the result of flushing of zeros. Otherwise you will get long sequences of 0. So this is the result of your encoded output sequence, where incoming bit is not 0. Remember, incoming bit is not 0, it is all ones, but still you are getting the output as 0 0. It is understood that if incoming bit is 0, you will get output as 0 0 only, because it will be keep on self looping in this state. But here it is not the case. Here the incoming bit is 1, but still you are getting output as 0 0. So this is the point, or this is a self loop which is disrupting the regular flow of the convolution encoder, and hence it is known as catastrophic codes. It's a catastrophe is of the result of the self loop. Okay. So comparing with all 0 output sequence, so if there is only 0 0 outputs, if you try to compare this sequence with all 0 0 output, the difference between these two is only in 4 bits. This one, and there is these two ones. So the Hamming distance between these two code sequence is just 4. Hamming distance is nothing but the number of bits in which two sequences are different. So with comparing with all 0 output sequence, the Hamming distance is only 4. We can summarize this catastrophic codes is the result of self loop with incoming bit is 1 but output is all zeros. This is a result where k input bits is not all zeros, but output is all zeros. So this is the characteristic of catastrophic codes. Our convolution encoder, or the structure of the encoder, should be such that it should be non-catastrophic. Otherwise we are going to end up in such problems in designing. Our all convolution encoders should be non-catastrophe of nature. This summarizes with the basic structure, understanding of or representation of convolution encoder codes. Thank you.